The conflicts between predictions and observations in Big Bang theory are not confined to what is widely known as the crisis in cosmology. Despite the ongoing popularity of this theory, essentially every prediction about the Big Bang theory is increasingly contradicted by ever-improving data. On the other hand, these observations are consistent with a non-expanding universe and the absence of a Big Bang. The real crisis in cosmology is that the Big Bang explosion never actually happened, and time has no starting point, or worse, it never existed. Hawking's perspective on this matter is encapsulated in his statement: "The universe has no clear bang. You can rewind to the earliest moments of existence, but asking what happened before would be like asking why you can keep going north when you reach the North Pole. Time, as we define it, loses meaning as the universe contracts. It never collapses to a single point, but no one has proven that physics operates that way. We always fear the unknown and are startled by the terrifying truths that we misconstrue. After all, what is time? Did the Big Bang happen? Join us in today's video, and don't be shocked when the information we're about to reveal will change your entire perspective on the past and the future. The universe came from nothingness. In 1981, many leading cosmologists from around the world gathered at the Pontifical Academy of Sciences, a landmark at the intersection of science and theology, nestled in an elegant villa within the Vatican Gardens. Stephen Hawking chose the backdrop of August to present what he would later consider his most significant idea, a proposal on how the universe could arise from nothingness. Before Hawking's presentation, all scientific or theological cosmological origin stories provoked the same question: what happened before that? For instance, the Big Bang theory, which was first introduced by the Belgian physicist and Catholic priest Georges Lemaitre, who later served as the president of the Vatican's Academy of Sciences, rewinds the expansion of the universe back to a hot, dense bundle of energy. However, the question remains: where did the initial energy come from? The Big Bang theory faces additional challenges. Physicists understand that an expanding ball of energy would evolve into a chaotic mess, rather than the vast, smooth universe observed by modern astronomers. In 1980, a year before Hawking's speech, cosmologist Alan Guth realized that issues with the Big Bang could be addressed by an additional factor: an initial exponential growth called cosmic inflation, which would make the universe vast, smooth, and flat before gravity had a chance to disrupt it. Inflation quickly became a leading theory for the origin of our universe. However, the problem of initial conditions persists. What is the origin of the tiny patch believed to have inflated into our universe, and what provided the potential energy to inflate it? Stephen Hawking, with his exceptional intelligence, proposed a solution to the never-ending quest to look back in time. He suggested that there is no beginning or end at all. During a Vatican conference, the physicist from Cambridge University, who was 39 years old at the time and still able to speak with his voice, addressed the audience and said, "There must be something truly unique about the universe's boundary conditions, and what could be more unique than the condition that there is no boundary?" The no-boundary proposal, fully presented in a 1983 paper by Hawking and his frequent collaborator James Hartley, envisions the universe in the shape of a sphere. Similar to a sphere with a diameter of 0 at its bottom point and gradually expanding as it goes up, the universe, according to the no-boundary proposal, smoothly expands from a point of 0 size. Hartley and Hawking formulated an equation describing the entire sphere, the wave function of the universe, encompassing the entire past, present, and future simultaneously, prompting contemplation on the seed of creation, the creative force, or any transitions from a time before. In one of his lectures at the Pontifical Academy in 2016, Stephen Hawking stated that the question about what existed before the Big Bang was meaningless. According to the no-boundary proposal, there is no concept of time available to refer to. Hawking compared this to asking what lies south of the South Pole, as both questions are invalid. Hartley and Hawking's proposal fundamentally redefined time. Each moment in the universe becomes a cross-section of the sphere. While we perceive the universe expanding and evolving from one moment to another, real time encompasses the relationships between the size of the universe in each cross-section and other properties, particularly entropy, or its disorder. Entropy increases from the bottleneck to the feather, pointing towards an emerging arrow of time. However, near the bottom of the sphere, the correlations become less reliable. Time no longer exists and is replaced by pure space. As Hartley, a professor at the University of California, Santa Barbara, explained recently over the phone, "We don't have birds in the early universe. Later we have birds. We don't have time in the early universe, but we have time later." Thus, time inherently lacks a starting point, a no-boundary condition version of space-time. Hawking proposed a timeless, boundaryless version. As you approach, the initial timeless state is replaced by imaginary time. In theoretical physics, the Hartley-Hawking state, named after James Hartle and Stephen Hawking, is a proposition related to the state of the universe before the Planck era. Hartley and Hawking suggested that if we could travel backward in time to the universe's origin, we would observe that very close to what could be the beginning, time gives way to space, initially consisting only of space and devoid of time. The inception is entities related to time. Since time did not exist before the Big Bang, the concept of the universe's origin becomes meaningless. According to the Hartley-Hawking proposal, the universe has no conventional origin. It is a singular point in both space and time before the Big Bang. Thus, the Hartley-Hawking state universe has no starting point, but it is not the steady-state universe of Hoyle. It simply lacks an initial boundary in both time and space. The Hartle-Hawking state is the wave function of the universe, a concept used to explore how the universe began, calculated from the Feynman path integral. More precisely, it is a hypothetical vector in the Hilbert space of quantum gravity theory that describes this wave function. It is a function of the metric tensor defined on the compact, D1, dimensional surface, the universe, where D is the space-time dimension. The exact form of the Hartley-Hawking state is the path integral over all d-dimensional geometries with the required boundary conditions on their boundaries. According to the theory, time separates from the three spatial dimensions, as we know it today, needs clarification. After the universe reaches the Planck age, a wave function of the universe like this can be shown to satisfy the Wheeler-DeWitt equation. Imaginary time is a mathematical representation of time appearing in some approaches to both special relativity and quantum mechanics. It finds applications in bridging quantum mechanics with statistical mechanics and in some cosmological theories. Mathematically, imaginary time is the real time that has undergone a Wick rotation, where its coordinate is multiplied by the imaginary unit I. Imaginary time is not imaginary in the sense of being unreal or fictitious, like challenging the logic of irrational numbers, but rather it is simply expressed in a form known as imaginary numbers by mathematicians. People might think this means imaginary numbers are just a mathematical game unrelated to the real world. However, from the perspective of empirical philosophy, one cannot definitively determine what is real. All we can do is find mathematical models that describe the universe we inhabit. It turns out that a mathematical model involving imaginary time predicts not only the effects we have observed but also effects we cannot measure yet but still have faith in for various reasons. So, what is real and what is imaginary? Is the difference only in our minds? In the theory of relativity, time is multiplied by I. This can be accepted as a characteristic of the relationship between space and time, or it can be incorporated into time itself as imaginary time, with the equations rewritten accordingly. In the physics of cosmology, imaginary time can be integrated into certain models of the universe, solutions to the equations of general relativity. Specifically, imaginary time can help smooth out singularities, where known laws of physics break down to eliminate these singularities and avoid such breakdowns. For example, the Big Bang appears as a singularity in ordinary time, but when modeled with imaginary time, that singularity can be removed, and the Big Bang operates like any other point in four-dimensional space-time. Before the Big Bang, there was nothing but an ocean of energy and time as well. It did not exist. The scientific evidence against the Big Bang. The debate over the issue of imaginary time among scientists ultimately returns to the fundamental question of the validity of the Big Bang. Since the launch of the James Webb Space Telescope in 2021, increasing evidence has been challenging the vagueness and gaps in this century's theory. Firstly, the emergence of light elements, lithium and helium. The Big Bang theory predicts that a certain amount of light elements, including lithium, helium, and deuterium, must have been created in the explosion believed to have formed the universe. For lithium, the prediction is 400 lithium atoms for every billion hydrogen atoms. However, astronomers have measured the abundance of lithium in old stars in our galaxy and found that the Big Bang prediction is not accurate. They know that stars formed very early in our galaxy's history because they contain a very small amount of iron and other heavy elements produced by pre-existing stars. In most of these stars, the abundance of lithium is only 160 lithium atoms per billion atoms, much lower than the Big Bang prediction. Moreover, with more data accumulated over the past few years, it's evident that older stars have less lithium. A recent study by Lerner, presented at the January 2020 meeting of the American Astronomical Society, indicated that observations of the abundance of both lithium and helium in current old stars deviate from predictions by over a dozen standard deviations, and the gap is widening at an accelerating rate. The oldest stars have less than half the amount of helium and less than a tenth of the amount of lithium, compared to the predictions of the Big Bang nucleosynthesis theory. The lowest observed lithium level is below 1% of the theoretical prediction. Indeed, the most consistent evidence is that neither helium nor lithium was formed before the first stars in our galaxy. Equally important is the research indicating that the observed abundance of these light elements has been predicted through an alternative explanation, proposing that these elements were created by stars in the earliest stages of the galaxy's evolution. This alternative explanation, referred to as the galaxy origin of light elements, or the Golay hypothesis by Lerner, stems from theoretical expectations that the first generation of stars formed in a galaxy would be of average mass, heavier by 4 to 12 times that of the Sun. These stars burn hydrogen into helium in tens to hundreds of millions of years, much faster than our Sun's burning rate of 10 billion years. The helium is then dispersed by powerful stellar winds in the final stages of these stars' life cycles. Cosmic rays from these primordial stars, colliding at high energies with other nuclei, create deuterium and lithium. Although this data entirely contradicts predictions about the Big Bang, they have been predicted and explained simply by theories of galactic evolution that exclude the Big Bang, including a paper published by Lerner in 1989. As known, lithium is created by cosmic rays emitted from early stars colliding with carbon and oxygen nuclei, as well as by stars in their giant phase. Lerner shows that similar stellar processes can account for the observed abundance of helium from nuclear reactions in early primitive stars and deuterium. The recent study, incorporating new calculations based on the GOL hypothesis, demonstrates that early stars not only produce the observed amounts of helium, deuterium, and lithium, but also generate other elements such as carbon, boron, and beryllium with observed quantities in the oldest stars. Lerner explains, The goal hypothesis was first published in full in my paper in 1989 and has been discussed by others before that. The predictions made in that published paper have been confirmed over many decades of subsequent observations. Unlike the predictions of the Big Bang hypotheses, the new work I am reporting at this conference makes the predictions more accurate and based on much broader knowledge that we currently have about the evolution of stars. These conclusions, based on observations of old stars in our galaxy, are reinforced by recent observations of conditions in newly forming galaxies. These galaxies are extremely bright, converting hydrogen into helium at rates hundreds of times faster than our current galaxy. Research from other scientists published last year showed that their brightness is controlled by stars with masses around 8 times the mass of the Sun, as predicted by the goal hypothesis. Structures too large to form in the time since the hypothesized Big Bang. The Big Bang theory proposes that the universe originated with an almost entirely homogeneous distribution of matter, uniform, and structures gradually formed from stars to galaxies and then conglomerated into superclusters. However, increasingly larger structures have been discovered earlier than expected. For example, in 2013, a group of observers, led by Roger Close, found a colossal collection of quasars spanning over 3 billion light-years, existing billions of years before. According to their perspective, it is too large to be created within the framework of conventional cosmology. Even larger galaxy structures were found in 2016 by Hirikoff and colleagues. Indeed, Lerner pointed out that, considering the current low velocities of galaxies, the large-scale structures of galaxy clusters that we observe would take hundreds of billions of years to form. In groundbreaking work in 1986, Lerner used plasma physics to predict the fractal structure of the universe, including structures with diameters of up to billions of light-years and structures discovered later. According to Lerner's theory, these structures could only form in a universe with a history stretching back more than 14 billion years. Another piece of evidence casting doubt among scientists is dark matter. The Big Bang theory predicts that most of the matter in the universe is dark matter, unlike any matter found on Earth. Increasingly sensitive experiments on Earth have failed to provide any conclusive evidence for the dark matter particles predicted by the Big Bang theory. Additionally, astronomical evidence has also ruled out dark matter. The simplest evidence is the relatively low speeds of galaxies in the universe. The large amount of dark matter predicted by the Big Bang would create gravitational forces that could cause galaxies to rotate at speeds of hundreds of km. However, the observed average speed is 50 km, eliminating the large amount of dark matter required for the Big Bang, as shown by Barishev, Silos Labini, Montuori, Pietronero, and Teiricurpi. The ultrafine distribution of dark matter needed to avoid high speeds is also incompatible with the clumpiness, inhomogeneity, of observed matter at all scales. Furthermore, the satellite galaxies of both the Milky Way and the nearby Andromeda Galaxy have disk-shaped configurations, as expected if gravity arises from ordinary matter. If gravity arose from dark matter, the satellites would have to be in a random sphere. This evidence is entirely inconsistent with the dark matter hypotheses, as demonstrated by Pavel Krupa and many other researchers. Perhaps most decisively, Ohm and Krupa in 2018 pointed out that the unavoidable effect of viscosity with dark matter would cause galaxy groups to merge quickly to a level that very few could observe, contrary to the existence of many such groups. Once again, there are simpler alternatives, not involving the Big Bang, to explain the data. Over 30 years ago, Peratt and Green demonstrated that electric forces would create constant rotation speeds in spiral galaxies, long used as the key evidence for dark matter. These speeds are measurements of the velocity of anisotropic plasma emitted in a galaxy, influenced more by electrical forces than gravitational forces. Jolacha, Bratek, and others have shown that in the outer regions of galaxies, including the Milky Way, the gas moves faster than the stars, and this difference can be explained by the influence of magnetic fields on the gas. More recently, Konkel and Covey provided persuasive evidence of the magnetic field's influence on the motion of stars. They discovered that a significant portion of stars nearby is embedded in filaments with lifetimes of hundreds of even GY. Although the authors did not draw this conclusion in their paper, it is clear that gravity alone cannot create long-lasting filamentary structures. However, magnetic fields with observed intensity can control the dynamics of dense gas filaments. And these filaments can, in turn, control the gravitational motion of stars within them. Magnetic fields, instead of assumed dark matter, can provide additional observable forces in galaxies. Surface brightness. The hypothesis that the expanding universe is the fundamental pillar of the Big Bang theory has faced challenges. Observations of the sizes and brightness of thousands of galaxies contradict predictions based on the expanding universe hypothesis, leading to a significant shakeup of this crucial pillar, as detailed in a paper in the monthly notices of the Royal Astronomical Society by lead scientist LBP Fusion Eric Lerner, titled Observations Inconsistent with Predictions of Galaxy Size and Surface Brightness Growth Based on the Expanding Universe Hypothesis. The study revealed that no predictions about the universe's expansion published regarding the growth of galaxy sizes align with actual data. All proposed physical mechanisms for galaxy development, such as galaxy mergers, also conflict with observations. However, the paper notes that the data align well with the contrary hypothesis that the universe is not expanding, and the red shift of light is caused by a different, currently unclear process. This research tests a prominent prediction from the 1930s regarding the Big Bang hypothesis, suggesting that objects at very distant distances should appear larger rather than smaller. According to the hypothesis, this is due to optical illusions caused by galaxies much closer emitting their light. This prediction was reiterated throughout the 1980s, but by the 1990s, the Hubble Space Telescope did not confirm that prediction. Instead, Hubble's images showed that the farthest galaxies appear smaller in reality. Subsequently, a group of researchers proposed an additional hypothesis that galaxies indeed grow in size over time. Therefore, very distant galaxies, when observed from billions of years ago, were theoretically much smaller than galaxies today. This way, the intrinsic sizes of galaxies in the 1990s, based on the developing galaxy theory, completely debunked the optical illusion predictions from the 1930s. In Lerner's paper, the quantified predictions from developing galaxy theories were tested based on the observed sizes of thousands of spiral and elliptical galaxies, using HST observations from 2004 to 2014. The paper limited the samples to galaxies with similar near-ultraviolet brightness. The observed data did not closely match predictions that galaxy sizes increase proportionally to the rate of universe expansion. Furthermore, Lerner pointed out that the process hypothesized for the development of elliptical galaxies, the merging with other galaxies, occurs at a rate almost 10 times slower than the growth rate proposed in the hypothesis. An even more severe inconsistency arises when comparing the gravitational mass of distant galaxies, calculated from their rotation speed and size, with the mass of the stars within them, calculated from their emitted light. Predictions about size based on the expanding universe theory lead to a gravitational mass smaller than the mass of the stars, which is inherently impossible. While predictions about the expanding universe do not align with the data, Lerner notes that predictions based on a non-expanding universe fit both spiral and elliptical galaxies at all distances, with an accuracy of a few %. Regardless of the distance, in a non-expanding universe, galaxies with a certain brightness have the same size, just as predicted by the non-expanding universe hypothesis. Lerner explains, in this hypothesis, The simple linear relationship between the redshift of light and distance is due to something happening to light as it travels, not the expansion of space. Currently, no one knows what could cause this, but the linear relationship and the non-expanding space make predictions that align with the data, whereas predictions about an expanding universe do not. The Big Bang theory has several issues that its supporters dismiss as anomalies. However, these issues contradict all the theory's predictions. To address this, supporters of the theory keep adding parameters to account for new data that doesn't fit. This has resulted in over 20 parameters being adjusted, and the theory cannot predict new results, which is a hallmark of a sound scientific theory. Recent results from the biceps instrument have led researchers to add even more parameters to the theory to explain contradictions between biceps and Planck results. On the other hand, hypotheses that align with a universe that had no beginning in time and no Big Bang can explain the data that contradicts the Big Bang theory in a much simpler way. The universe is a truly fascinating and awe-inspiring place. With its seemingly endless expanse of stars, galaxies, and other celestial bodies, it's easy to feel small and insignificant. However, despite its vastness, the universe has always captivated the imagination of humanity. From the earliest stargazers to the most advanced scientists of today, we have always been drawn to explore the mysteries of the cosmos. Where's the edge of the observable universe? And what's beyond? What lies outside the boundary of the universe? Join us as we embark on a journey into the abyss of this universe, where darkness itself fears to exist. The Big Bang tells us that at some point in the distant past, the universe was hotter, denser, and expanding much more rapidly than it is today. The stars and galaxies we see throughout the universe in all directions only exist as they do because the universe has expanded and cooled, allowing gravitation to pull matter into clumps. Over billions of years, gravitational growth has fueled generations of stars and the formation of galaxies, leading to the universe we see today. Everywhere we look, in all directions, we see a universe that tells us the same cosmic story. But part of that story is the fact that the farther away we look, the farther we're looking back in time. The universe hasn't been around, forming stars and growing galaxies, forever. According to the Big Bang and the observations that support it, the universe had a beginning. In the early stages after the Big Bang, the universe was filled with a variety of ingredients, and it began with an incredibly rapid initial expansion rate. These two factors, the initial expansion rate and the gravitational effects of everything in the universe, are the two head-to-head players in the ultimate cosmic race. On the one hand, the expansion works to push everything apart, stretching the fabric of space and driving the galaxies and the large-scale structure of the universe apart. But on the other hand, gravitation attracts all forms of matter and energy, working to pull the universe back together. Normal matter, dark energy, radiation, neutrinos, black holes, gravitational waves, and more all play a role in the expanding universe. The expansion rate began large, but has been decreasing as the universe expands. There's a simple reason for this. As the universe expands, its volume increases, and therefore the energy density goes down. As the density drops, so does the expansion rate. Light that was once too far away from us to be seen can now catch up to us. This fact carries with it a huge implication for the universe. Over time, galaxies that were once too distant to be revealed to us will spontaneously come into view. It may have been 13.8 billion years since the Big Bang occurred, but with the expansion of the universe, there are objects as far away as 46.1 billion light-years whose light is just reaching us. All told, if we were to add up all the galaxies that exist within this volume of space, we'd find there are a whopping 2 trillion of them within our observable universe. As enormous as this number is, it's still finite, and our observations don't reveal an edge in space in any direction we look. The amount of time that's passed since the Big Bang, the speed of light, and the ingredients in our universe determine the limit of what's observable. Any farther than that, and even something moving at the speed of light since the moment of the hot Big Bang, will not have had sufficient time to reach us. But all of this will change in time. As the years and aeons tick by, light that was unable to reach us will finally catch up to our eyes, revealing more of the universe than we've ever seen before. Today, we see the universe as it exists 13.8 billion years after the hot Big Bang. Most of the galaxies we see are clumped together in galactic groups, like the Local Group, and rich clusters, like the Virgo cluster, separated by enormous regions of mostly empty space known as cosmic voids. The galaxies within these groups are a mix of spirals and ellipticals, where a typical Milky Way-like galaxy forms an average of about 1 new sun-like star per year. But as we look farther and farther away, we start to see how the universe grew up to become this way. As we look to greater distances, we find that the universe is slightly less clumpy and slightly more uniform, particularly on larger scales. We see that galaxies are lower in mass and less evolved. There are more spirals and fewer elliptical galaxies. On average, there are greater proportions of bluer stars, and the star formation rate was higher in the past. There's less space between galaxies on average, but the overall masses of groups and clusters is smaller at earlier times. It paints a picture of a universe where today's modern galaxies were created by smaller, lower mass galaxies, merging together over cosmic timescales, building themselves up to become the modern-day behemoths we see all around us. The universe, at earlier times, consists of galaxies that are physically smaller, lower in mass, closer together, larger in number, bluer in color, richer in gas, with higher rates of star formation and with fewer proportions of heavier elements as compared to today's galaxies. But as we go farther and farther away, to earlier and earlier times, this gradually changing picture begins to transform abruptly. When we look back to a distance that's presently 19 billion light-years away, corresponding to when only the 3 billion years had passed since the hot Big Bang, we see that the universe's star formation reached its maximum, about 20 to 30 times the rate at which new stars are formed today. An enormous fraction of supermassive black holes are active at this time, emitting enormous amounts of particles and radiation due to the consumption of surrounding matter. For the past 11 billion years or so, the universe's evolution has been slowing down. Sure, gravitation continues to collapse structures, but dark energy begins to work against it, coming to dominate the universe's expansion more than 6 billion years ago. New stars continue to form, but the peak of star formation is in our distant past. And supermassive black holes continue to grow, but shone at their brightest earlier on, with a greater fraction of them fainter and inactive today than during these early stages. As we go to greater and greater distances closer to the edge defined by the start of the hot Big Bang, we start to see even more significant changes. When we look back to distances of 19 billion light-years, that corresponds to a time when the universe was just 3 billion years old, star formation was at its peak, and the universe was maybe 0.3 to 0.5% heavy elements. But as we close in on 27 billion light-years away, the universe was only 1 billion years old. Star formation was much smaller, as new stars formed at rates approximately a quarter of what they'll be later on at their peak. The percentage of the normal matter that's made of heavy elements plummets precipitously to 0.1% at an age of 1 billion years, and to just 0.01% at an age of around 500 million years. Rocky planets in these early environments may well have been impossible. Not only was the cosmic microwave background significantly hotter, it would have been at infrared rather than microwave wavelengths, but every galaxy in the universe should be young and full of young stars. There are likely no elliptical galaxies this early on. Going farther back than this really pushes the limits of our current instrumentation, but telescopes like Keck, Spitzer, and Hubble began to take us there starting in the 1990s. Once we go back to distances of approximately 29 billion light-years or farther, corresponding to times where the universe was 700 to 800 million years old, we start to run into the first edge of the universe, the edge of transparency. We take for granted today that space is transparent to visible light, but that's only true because it isn't full of light-blocking material like dust or neutral gas. But at early times, before enough stars had formed, the universe was full of neutral gas and hadn't become fully ionized by the ultraviolet radiation from these stars. As a result, a lot of the light we see is obscured by these neutral atoms, and it's only once enough stars have formed that the universe becomes fully ionized. This is, in part, why infrared telescopes, such as NASA's newest flagship mission, the James Webb Space Telescope, are so crucial to investigating the early universe. There's an edge to where we can see in the wavelengths we're familiar with. At distances of 31 billion light-years, corresponding to a time of just 550 million years after the Big Bang, we reach the edge of what we call rionization, where the majority of the universe is mostly transparent to optical light. Rionization is a gradual process and takes place unevenly. It's like a jagged, porous wall in a lot of ways. Some places see this rionization happen earlier, which is how Hubble spotted its most distant galaxy ever. But other regions remain partially neutral until nearly a billion years have passed. James Webb has now taken us even farther, showing us galaxies as far back as 330 million years after the Big Bang, where they still appear large, evolved, and are not quite pristine in terms of the elements that are present within them. There must still be stars and galaxies out there beyond even what the Webb telescope has shown us so far. Beyond those limits of what our current telescopes can see, however, we can still measure the indirect signs that stars have formed. Through the emission of light from hydrogen atoms themselves, which only occurs when stars form, ionization occurs, and then the free electrons recombine with the ionized nuclei, emitting light in the aftermath of that. Right now, we only have the indirect signatures of this signature of early star formation, although there are many that dispute the validity of this signal, indicating that young galaxies existed as early as 180 to 260 million years after the Big Bang. These proto-galaxies formed enough stars that we can see the first hints of their existence buried in the data, corresponding to a distance of between 34 and 36 billion light-years away. Although our current telescopes haven't seen these galaxies directly, the great expectation of many astronomers is that a long enough deep-field exposure with James Webb will reveal them. However, there are likely still sources of light, and the first ionized regions of space in the universe, going back even before that. The very first stars of all, in the rare regions that grow in mass density the fastest, are expected to come about between 38 and 40 billion light-years away, corresponding to times just 50 to 100 million years after the Big Bang. Before that, the universe was only dark, full of neutral atoms and radiation from the Big Bang's leftover glow. Going back even farther, we fully expect there to be additional edges of interest. 44 billion light-years away, the radiation from the Big Bang was so hot that it becomes visible. If a human eye were to exist, it would be able to see that radiation begin to glow red, similar to a red-hot surface. This corresponds to a time just 3 million years after the Big Bang. If we go back to 45.4 billion light-years away, we come to a time just 380,000 years after the Big Bang, where it becomes too hot to stably maintain neutral atoms. This is where the leftover glow from the Big Bang, the cosmic microwave background, originates from. If you've ever seen that famous picture of the hot and cold spots from the Planck satellite, this is where that radiation originates. And before that, 46 billion light-years away, we come to the earliest stages of all, the ultra-energetic state of the hot Big Bang, where the first atomic nuclei, protons and neutrons, and even the first stable forms of matter were created. At these stages, everything can only be described as cosmic primordial soup, where every particle and antiparticle in existence can be created from pure energy. However, what lies beyond the frontier of this high-energy soup remains a mystery. We have no direct evidence for what occurred in those earliest stages, although many of the predictions of cosmic inflation have been indirectly confirmed. The edge of the universe, as it appears to us, is unique to our perspective. We can see back 13.8 billion years in time in all directions, a situation that depends on the space-time location of the observer who's looking at it. The universe has many edges: the edge of transparency, the edge of stars and galaxies, the edge of neutral atoms, and the edge of our cosmic horizon from the Big Bang itself. We can look as far away as our telescopes can take us, but there will always be a fundamental limit. Even if space itself is infinite, the amount of time that's passed since the hot Big Bang is not. No matter how long we wait, there will always be an edge that we'll never be able to see past. In other words, the universe is big. Really big. Bigger than the most we can comprehend. The observable universe extends from the Earth to the horizon of the cosmic microwave background. When the light of the cosmic background was emitted about 13.8 billion years ago, it was only 42 million light-years away, but because of the expansion of the universe, that horizon is now more than 46 billion light-years away. Using that definition, the known universe is about 93 billion light-years in diameter. As large as that is, it's only the portion of the universe we can observe. The total universe extends beyond our horizon. Just how far it goes is an interesting question. There are indications that the universe extends far beyond what we can observe. The universe we see has a fairly uniform distribution of matter. Sure, matter clumps into galaxies, and those galaxies clump into clusters of galaxies, but on a scale larger than about 300 million light-years, those clusters appear randomly distributed. In other words, it is homogeneous and isotropic. If what we observe were the extent of the universe, then we would be basically in the center. Since we see about the same amount of mass in all directions, the gravitational pull from all that matter would basically cancel out. But for a galaxy on the edge, it would see a great deal of matter in one direction and basically nothing in other directions. Gravitationally, it would be pulled toward the center of the universe. Because of dark energy, this universe wouldn't collapse upon itself, but it would mean that galaxies would tend to clump toward the center. Since gravity is a curvature of space-time, this would distort the overall shape of the universe. What we observe, however, is that the universe is flat. At the very least, this means an observer at the edge of our horizon must also see a homogeneous and isotropic universe. Given the flatness limit, that would mean the total universe is at least 400 times larger than the observable universe, but it could be much larger. Another point of evidence is the fact that the cosmic microwave background has an almost perfectly uniform temperature. There are small fluctuations of temperature throughout the background, but the overall temperature is the same in all directions. The thing is, it shouldn't be. The cosmic microwave background was emitted when the universe was about 380,000 years old. At best, that means that only regions of space within a radius of 380,000 light-years would have any way to reach thermal equilibrium. For anything more distant, there simply wasn't enough time for the regions to communicate, even at the speed of light. When we look at the cosmic background in different directions, we can see different regions that couldn't have reached the same temperature. They were simply too far away from each other, and yet they have the same temperature. What gives? The dominant idea is known as early inflation. Basically, a fraction of a second after the Big Bang, the universe entered a short period of extremely rapid expansion. In a brief moment, the universe expanded by a factor of 10 to the power of 60 before settling down to its current rate of expansion. While we don't have direct evidence of early inflation, it does agree with several observational aspects. According to the inflation model, the observable universe was roughly the size of a quark before early inflation and about the size of a grain of sand afterwards. If the size of the total universe before inflation was the distance light could travel since the Big Bang, then the current universe is about 10 to the power of 27 larger than the observable universe. In other words, comparing the observable universe to the entire universe is like comparing a grain of sand to the observable universe. It could be much larger, perhaps even infinite. Of course, all of this assumes the cosmos doesn't have some kind of strange topology. Since space and time can warp and weft, one could imagine a universe that loops around to itself, being finite in volume, but infinite in distance. Imagine a cosmic version of the surface of the Earth. It has a finite area, but due to the Earth's curvature, you could travel in a particular direction forever, simply looping around the Earth over and over. In cosmic terms, that would mean a beam of light traveling through space would eventually find itself back where it started. If the universe were closed and smaller than the observable universe, we would expect to see multiple versions of the same galaxies. There have been studies looking for periodic fluctuations in the cosmic microwave background that would indicate such a closed universe effect, and they've found no evidence of such a thing. If the universe is truly closed, then it must be at least 78 billion light-years in diameter. Of course, there is no reason to presume the universe has such a closed topology, so that lower bound should be taken with a grain of salt. So the short answer for the size of the universe is that it's huge. Likely very, very, very huge. Possibly infinite. On the other hand, note that the universe is not only vast, but also mysterious, filled with wonders beyond our comprehension. Only 5% of the universe is normal, observable matter. The remaining 95% of the universe is stuff that we can't see, don't yet understand. An extraordinarily vast portion of the cosmos is still unknown. Despite the technological advancements of the last century, even with computers at our fingertips, and the worldwide internet and space-based observatories mapping the far reaches of our universe, there is still so much that we don't understand. Worse, the problems facing our picture of the universe are not limited to what we can perceive. Our mind and the culture in which it was formed condition the way we explore the universe. Because of this particular conditioning, we have mental blind spots for the cosmic phenomena that run counter to human intuition and understanding. For instance, Turner claims that the mind is predisposed to see things as statistically significant when they might not be. We erroneously perceive patterns in the spacing of stars and of the planets in the solar system, seeing them as though they were arranged. Furthermore, there are other properties of the mind that get in the way of seeing the truth. Consider, for instance, our belief that massive objects must take up space. It is not a direct relationship. We accept that a piece of lead is more massive than a pillow, even though the latter is larger. At the extremes, however, we expect some positive correlation between the two. The extreme physical environment of a neutron star then poses problems. As Michael Strauss suggests, the star is so dense that a thimbleful of neutron star material has the mass of 70 million elephants. We cannot help but wonder, where is all the mass? Obviously, we are blinded by being human when we look at something larger than the human experience. It becomes further apparent when we are confronted with counterintuitive phenomena like white dwarfs and black holes. White dwarfs decrease in size as they become more massive, says Joshua Wynne. And for black holes, all mass is compressed to zero size. While we cannot see the black hole, giving the phenomena a name allows us to imagine it. The same could be said of dark matter and dark energy. As with the previous analogy, language provides a means of overcoming our initial blindness to interact with these cosmic phenomena. After all, the universe was not built for the human mind to understand. When we look up at the night sky, we see only a tiny fraction of what is out there. It is the task of the astrophysicist to develop a picture of the universe despite our overwhelming blindness.
In 1930, the concept of dark matter and dark energy was first introduced by Fritz Zwicky. The influence of these two sources of matter and energy on the formation of stars and galaxies has been supported by numerous observations and discoveries in modern cosmology. However, every cosmological model has its own shortcomings. The unique existence of an ancient galaxy completely devoid of dark matter is a significant blow to the astronomical community. It is challenging the efforts of scientists to answer the question, where does the origin and existence of the universe come from after billions of years? The presence of a dark matter-free galaxy raises many hypotheses about humanity's understanding of the vast 95% of the universe. Does this affect the process of sustaining the existence of the galaxy itself? And what does the future hold in store for us? Does dark matter truly exist, or is it just an excuse, a condition for the current limitations of humanity's knowledge? Let's explore the latest discoveries in this field to gain a deeper understanding of the vast universe and the significance of dark matter in maintaining the existence of magnificent galaxies. This is EYES 200M, and welcome back to join us on this journey. NGC 1277, the relic of the primordial universe. Dark matter and ancient galaxies. It's the enigma that has puzzled many scientists and astronomers of the 21st century. Discovering and observing these distant remnants is incredibly challenging due to the limitations of scientific technology. However, thanks to the presence of the James Webb Space Telescope, or JWST, humanity has been able to venture further in the search and exploration of the oldest relics in the universe, galaxies formed shortly after the Big Bang. Before the JWST embarked on its noble mission, NGC 1277 was just one of the faint red smudges in the southern sky as seen through the lens of the Hubble telescope. It was one of over 700 ancient galaxies captured by James Webb in early June. NGC 1277 is a dwarf elliptical galaxy located in the constellation of Andromeda. It is a member of the Perseus cluster and lies approximately 220 million light-years away from us. NGC 1277's apparent magnitude is around 14.7. It was discovered on December 4th, 1875, by Lawrence Parsons, the 4th Earl of Rosay. NGC 1277 is unique in that it is considered a relic of what galaxies were like in the early universe. The galaxy is composed exclusively of aging stars that were born 10 billion years or so ago. But, unlike other galaxies in the local universe, it has not undergone any further star formation. Astronomers nickname such galaxies as red and dead because the stars are aging and there aren't any successive generations of younger stars. The telltale sign of the galaxy's arrested development lies in the ancient globular clusters that swarm around it. The reddish clusters are the strongest evidence that the galaxy went out of the star-making business long ago. Otherwise, there would be a lot of blue globular star clusters, which are largely absent. The lack of blue clusters suggests that NGC 1277 never grew further by gobbling up surrounding galaxies. To be fair, our understanding of the grand relics of the universe, like NGC 1277, is far too limited. Before shocking the world with its meager dark matter content, NGC 1277 had perplexed many scientists with data concerning the supermassive black hole residing at its core. Recent findings indicate that the black hole at the center of the galaxy NG 1277 seems to account for about 59% of the total galaxy mass, the largest fraction of any supermassive black hole ever measured. It harbors a black hole with an approximate mass of 12 billion times that of our Sun. This far exceeds the expected mass of the central black hole in a galaxy of the modest dimensions of NGC 1277. We suggest that this giant black hole was ejected from the nearby giant galaxy NGC 1275 and subsequently captured by NGC 1277. The ejection was the result of gravitational radiation recoil when two large black holes merged following the merger of two giant ellipticals that helped to form NGC 1275. The black hole wandered into the cluster core until it was captured in a close encounter with NGC 1277. The migration of black holes in clusters may be a common occurrence. Most massive galaxies have supermassive black holes at their centers, and the masses of the black holes are believed to correlate with the properties of the host galaxy bulge component. Several explanations have been proposed for the existence of these locally established empirical relationships, including the non-causal statistical process of the galaxy merging, direct feedback between the black hole and its host galaxy, and the subsequent violent relaxation and dissipation. The empirical scaling relations are therefore important for distinguishing between various theoretical models of galaxy evolution, and they furthermore form the basis for all black hole mass measurements at large distances. Observations have shown that the mass of the black hole is typically 0.1% of the mass of the stellar bulge of the galaxy. Until now, the galaxy with the largest known fraction of its mass in its central black hole, 11%, was the small galaxy NGC 4486 B1-9. From observational experience, the existence of the central black hole in NGC 1277 remains a significant mystery. It is still unclear whether these galaxies represent the tail end of distribution, or if galaxies with dominant central black holes deviate from the typical mass black hole relationship seen elsewhere. When James Webb focused its observation on NGC 1277, scientists immediately recognized a significant issue from the images. The existence of a massive black hole led to parameters indicating that NGC 1277 is entirely devoid of dark matter. Is this a normal relationship in the universe, or are there still hidden secrets? Can black holes truly consume even the components known as dark matter? Or, fundamentally, does dark matter and dark energy not exist? If you are truly curious about what dark matter and dark energy have done to sustain the existence and formation of galaxies, I encourage you to check out the video James Webb Unveils the Mysterious Link Between Dark Energy and Black Holes in the Formation of Ancient Galaxy Clusters on our channel. The link will be provided right below the description for you. But for now, let's delve into the evidence from NGC 1277 to discover what is truly happening inside this ancient galaxy. I hope you'll keep an open mind, as what we are about to reveal may challenge some of your beliefs, what you've heard, and what you've learned so far. NGC 1277 has a severe dark matter deficiency. In the current standard model of the universe, dark matter and dark energy account for approximately 95% of the total mass in the universe, meaning only about 1/6 is composed of the ordinary matter that we interact with in our daily lives. Dark matter remains elusive. It does not interact like regular matter, and its existence is solely inferred from its gravitational effects on stars and gas in galaxies. According to the Lambda CDM cosmological model, present-day galaxies with stellar masses greater than 100 billion times that of the Sun likely contain a substantial amount of dark matter within their stellar bodies. Models indicate that in massive early-type galaxies, or ETGs, with masses around 115 billion times that of the Sun, dark matter must account for approximately 15% of the dynamic mass within one effectual radius, or 1 RE, and about 60% within 5 REs. Most giant ETGs, or early-type galaxies, have been shaped through a two-phase process: a rapid formation of a compact core, followed by the accumulation of an extended outer envelope through mergers. Extremely rare galaxies have managed to avoid the second phase, known as relic galaxies, believed to be the frozen remnants of giant ETG populations at Z is greater or less than 2. The best-known candidate for a relic galaxy discovered so far is NGC 1277, located in the Perseus cluster. NGC 1277 is a relic galaxy, a galaxy that does not interact with neighboring galaxies. Relic galaxies are exceedingly rare and are considered vestiges of giant galaxies formed in the early universe. Scientists have utilized data from the George and Cynthia Mitchell spectrograph, or GCMS, Deep Field Integral Field Spectroscopy, to re-examine NGC 1277 at an unprecedented radius of 6 kpc, equivalent to 5 effective radiuses, or 5 REs. By employing a model called anisotropy genes modeling, they found that dark matter contributes insignificantly within the range of 5 REs, which contradicts the predictions of the Lambda CDM cosmological model, Cameron explained. The significance of relic galaxies in helping us understand the formation of the early universe is the reason why we decided to observe NGC 1277 using integral field spectroscopy. From the spectra, we constructed dynamic maps that enabled us to understand the distribution of mass within the galaxy up to a distance of approximately 20,000 light-years. According to their findings, NGC 1277 contains no more than 5% of dark matter. Its mass distribution is solely determined by its stars. Current cosmological models predict that a galaxy of this size should have been between 10 to 70% dark matter. Dr. Ignacio Trujillo, a researcher at IAC and ULL, stated, "The discrepancy between the observations and what we expected is a puzzle, and it may even pose a challenge to the standard model." The research team proposed two possibilities to explain the lack of dark matter in NGC 1277. Dr. Anna Ferre-Matau, also from IAC and ULL, added, "One possibility is that gravitational interactions with the surrounding environment in the galaxy cluster containing this galaxy have stripped away the dark matter. The absence of an extended outer envelope reduces dynamical friction and prevents the accumulation of the outer layer. Therefore, Dr. Ferre-Matau suggests that NGC 1277 may have lost its dark matter very early on, or that it never had much dark matter to begin with. Scientists are currently discussing their discovery within the context of recent proposals, suggesting that some relic galaxies may result from dark matter being stripped away as they fall into and interact with galaxy clusters. Moreover, NGC 1277 could have been formed through a high-speed collision of gas-rich progenitor galaxy fragments, where dark matter left behind a dispersed baryonic disk. Standard calculations suggest that a relative velocity of about 2,000 kilometers per second or so is needed for the second process to occur, and this could plausibly take place in the ancestors of today's rich galaxy clusters. The issue remains that dark matter could have been expelled from the system during the galaxy's formation through the merging of progenitor galaxy fragments, resulting in a relic galaxy. However, both theories have left researchers unsatisfied. Cameron stated, "The puzzle of how a massive galaxy could form without dark matter remains an enigma." They plan to continue observations using the William Herschel telescope at the Roque de los Muchachos Observatory on the Canary island of La Palma. Perhaps surprisingly, the clear absence of dark matter in NGC 1277 is further evidence for its existence and raises significant doubts about alternative theories proposed to explain the observed effects in galaxies, such as theories suggesting a slight modification of the law of gravity on large scales. While dark matter may be missing in specific galaxies, a modified law of gravity must be universal. It cannot have exceptions. Therefore, a galaxy without dark matter would reject this alternative dark matter hypothesis. This presents a challenge to the Lambda CDM model itself. How many more secrets are hidden in the universe? Are we behaving like those who condemned Galilee? The truth is that the universe is too wide and contains too many questions. That's why I asked you to keep an open mind, because we will see many other great changes. The relationships between dark matter, dark energy, and ancient galaxies. Dark matter and dark energy are believed to have influenced the formation and evolution of galaxies during the early epochs following the Big Bang. Although they remain subjects of ongoing research and are not yet fully understood, hypotheses about dark matter and dark energy have been proposed to explain certain physical phenomena that cannot be accounted for by ordinary matter and energy. According to current physical models, dark matter is assumed to exert gravitational effects and play a crucial role in the formation of large structures in the universe, including galaxy clusters and cosmic filaments. Dark matter enhances the gravitational force in the universe, leading to the contraction and concentration of matter to form galaxies. Dark energy, on the other hand, is believed to have a repulsive effect on distant galaxies, contributing to the cosmic expansion between galaxies. Dark energy is a concept devised to explain the accelerating rate of expansion of the universe and why galaxies rotate around their axes at a certain speed without breaking apart due to centrifugal forces. According to this hypothesis, dark energy can provide an additional push, contributing to the formation of galaxy clusters and cosmic filaments. Dark energy enhances the gravitational force between objects in the universe, leading to the formation of large structures and uneven distribution of matter in space, resulting in the network of galaxies that we observe today. But how do we find them? Those entities that do not interact with regular particles and assert their role? Well, the answer lies in the past, with a fascinating journey that starts from the Coma Cluster. The Coma Cluster, also known as the Coma-Abel 1656 cluster, is one of the nearest and largest galaxy clusters that we know of. It lies in the constellation Coma Berenices and is approximately 320 million light-years away from Earth. It is also one of the richest galaxy clusters in the nearby universe. The Coma Cluster has an incredibly high galaxy density and contains many massive galaxies. On average, each volume of space within the cluster hosts about 10 to 15 galaxies. This means that in each smaller volume of the cluster, there exists a large number of galaxies clustered closely together. Well, what does this mean? According to the gravitational theory in physics, large galaxies within the Coma Cluster could move and merge within smaller galaxies at high speeds. However, galaxies within the cluster maintain stable velocities, and close galaxies can still avoid collisions and mergers. This contradicted previous calculations by space physicists. Hence, the concept of dark energy and dark matter emerged. According to the theory, dark matter interacts with regular matter through gravitational force. The presence of the matter in the Coma cluster has caused galaxies to move slower than what was predicted by the gravitational force of regular matter alone. In the research paper, Strong and Weak Lensing United, the mass distribution of the merging galaxy cluster, 1 IES 0657-558, derived from joint X-ray and lensing analysis. Scientists used strong and weak lensing measurements to determine the mass distribution within the Coma cluster. The research findings revealed the existence of dark matter in the cluster and its significant impact. As a result, we were able to ascertain the presence of a substantial amount of dark matter, estimated to make up around 90% of the mass of Coma. So, dark matter acts as a counterbalance, like a scale on the other side, to be in equilibrium with gravitational force. Put simply, if we were to remove dark matter, we would witness billions of galaxies colliding with each other every day. They would stop rotating around their axes and rush away from each other every second. Earth would also rush straight towards the Sun and become a part of it. This equilibrium has been maintained for billions of years since the birth of the universe. Evidence of this balance still exists in the images captured by the James Webb Space Telescope. There is only one reason to explain the current situation, and that is that we made a mistake right from the step of determining the types of particles and energy that make up the galaxies. We have been wrong from the very beginning of our theories. Scenarios of ancient galaxy formation. According to previous cosmological models, galaxies would continuously evolve and form new stars. However, without dark matter, the sources of energy to form new stars would be limited. As a result, galaxies would lack younger star generations, and the existing stars would continue to age without any replenishment. Early proposed scenarios for the formation of large primordial galaxies indicated a monolithic collapse similar to what was suggested for the oldest stellar populations in the Milky Way. However, these models have become outdated with the emergence of cold, dark matter formation models in cosmology. Recent computational studies based on the Lambda CDM cosmological framework, however, suggest that nature borrows from both scenarios, and the process of forming massive ETGs, again, early-type galaxies, can be divided into two stages. Initially, the giant ancestors of ETGs undergo a dissipation-less collapse, resulting in a compact rotating object where star formation is quickly suppressed, possibly due to the activity of an active galactic nucleus, or AGN. In the second stage, the massive evolution of the stellar population transforms the blue-hued objects into red, and most of the stellar mass growth of the object comes from the accumulation of an extended outer shell supported by pressure through dry accretion. The account of this simplified two-phase formation is supported by observations indicating that galaxies evolve passively at higher redshifts, being much more compact than local massive ETGs, and they have grown 4 times in effective radius since redshift, or z is infinity more than 2. This framework is supported by the fact that stellar shells have been demonstrated to develop over cosmic time. Additionally, recent identifications of small, compact, star-forming and likely rotating super-red nuggets might provide further evidence for the two-phase formation scenario. Detailed studies of NGC 1277 have provided a unique and profound insight into the harsh conditions where nuggets develop. Martin Navarro and colleagues discovered that the initial mass function, or IMF, of NGC 1277 is the heaviest across all galaxies, implying a high mass-to-light ratio of stars. Similarly, slightly less extreme properties have been confirmed for two other relic galaxies. Furthermore, dynamical modeling revealed that almost no dark matter is needed to explain the dynamics of stars within the innermost 13 inches of NGC 1277. Conclusion. Thus, the relationship and correlation between dark matter and galaxies remains a mysterious puzzle that requires further exploration. The discoveries about NGC 1277 have provided valuable insights into the formation and evolution of relic galaxies. The evidence and models have revealed surprising and intriguing aspects concerning the dynamics, central black holes, and the development of dark matter in the universe. If you are still curious and eager to explore more about the latest discoveries in this field, stay tuned for our James Webb video about the enigmatic connection between dark energy and black holes in the formation of ancient galaxy clusters. In the meantime, we sincerely thank you for joining us today on this journey. Keep following and discovering the fascinating and novel aspects of the universe in the future. See you in upcoming videos. Thank you and have a wonderful day.